We're going to use the quotient rule to simplify square roots. Now, of course, there's a product rule we could use and a quotient rule. And of course, you can apply these to any kind of root, any kind of index. But specifically here, we're going to focus on the quotient rule only for square roots. Now, that actually says we have it here. As long as the b is not equal to 0, if you take the square root of a over b, you can apply a square root on the top and you can apply a square root on the bottom. And then you can go from there. All right, so we're going to apply that to this first example. This means that we can take the square root of 121 and over the square root of 225. And then we can apply the square root top and bottom separately. Square root of 121, 11 times 11 is 121, which means that the top is going to turn into an 11, and the bottom one, the square root of 225 is 15. So we have 11 over 15, and that can't be reduced anymore. That would be your answer for the first one. So you just apply a square root on the top and square root on the bottom. But these next two examples we're looking at here, these are ones where we have to break this down further because square root of 80 is not a perfect square. So for these, we're still going to start with the same step we did before. We are going to apply a radical on top and a radical on the bottom. Now the bottom one we can do. Square root of 49 is 7, so that one's done. Now let's work with the 80. Now the 80, what we want to try and do is break this up into a product of two numbers to where one of them is a perfect square. Particularly, you're trying to find the highest perfect square. Now you may not know what that is with 80, so let's start by breaking this down. So 80 could be written up as 4 times 20 we can do. That's one possibility. And 4 goes into 2 and 2. 20 is going to be 2 times a 10, and 10 is going to be 2 times 5. Now, if I take a look at the primes I have left over here, I get 2 times 2 times 2 times 2 times 5 as a result. Okay, so all these right here, 2 multiplied 4 times is 16, and 16 is a perfect square. So this is actually the way I want to write this. I want to write it as 16 times 5. Of course, if I would have chose to divide this by 5 right away, I would have gotten 16 and recognized that that's a perfect square. But that's not always going to happen. I just wanted to show you this way to where if you went about it a different way with a factor tree, you still would arrive at the same result because you get the same number of primes multiplied together here. So 2 to the 4th power is 16, and you get that. Now we're doing that purposely because now we can break these radicals up and do radical 16 times radical 5, 7 on the bottom. The square root of 16 becomes a 4. And so now that's going to be your answer. You get 4 square root of 5 over 7. There's nothing you can do more as far as that. The square root has to stay as part of your answer. Now let's do the same thing with the 108. Okay, so again, if you have that, we'll first start by writing it out as square root of 108 over the square root of 25. And we get a 5 on the bottom there, but the 108 is one where we want to go ahead and work with that one. So let's do that here. 108, if you divide it by 2, you're going to get 2 and 54. And then the 54, you can break that down. You might think of 6 and 9 right away. So that would be a 2 and a 3. And then that would be another 3 and a 3 there, which means that 108 is equal to 2 times 2 times 3 times 3 times 3. Now what you want to do is look for pairs here. Every time you get a pair, that's going to give you a perfect square. So here, this is a 4, and this is going to be a 9. Both of those would be perfect squares. However, if you multiply 4 times 9, you'll get 36, which is another perfect square, which means that that would be the largest perfect square you could write with this. So 108 can be written as 36 times 3. So now I can do square root of 36 times the square root of 3. And that means that when it breaks down, you're going to get a 6 square root of 3 over 5. And so now that would be the way you break this down. Again, square root of 3, you can't do any more with that one. Let's do one more of those here. Let's do this. Okay, we have square root of 363 over square root of 3. All right. So now, again, if you're not sure what to do on this, so this is already broken down for us. We can't do anything with square root of 3. Now, what you might think about doing first is maybe use a calculator and see if 363 divided by 3 goes in evenly. And actually, it does in this case. So this is a case where I want to use the quotient rule in reverse. Instead of having it in a separated form like this, and I would know to go further because I can't do anything with the square root of 3. That's why I thought of perhaps we can combine this together. So what I'm going to do instead is do this. I'm going to do 363 over 3 instead there. Now, because I did it that way, now I can divide those, and I get the square root of 121, and square root of 121 is 11. So now I was able to get the right answer on that. So again, this is using the quotient rule kind of in reverse. I took the separated square roots and I put them together as one single square root. That would allow me to divide and do more to simplify.